There we go. I will. I will begin with a word of prayer. So, here we go. Dear Father, we thank you for this day. I thank you for these students. Just ask you to just bless our work today, Lord. In your name I pray. Amen. Okie doke. So we are talking about orthogonal orthogonality, right? And so our basic goal today is to understand what does it mean for a set to be orthogonal, and if a given set's not orthogonal, can we make it orthogonal by some sort of like process? Is there a way to create an orthogonal set from a non-orthogonal one? These are things we're after today. So first of all, what's the definition of orthogonal? Perpendicular, yeah. So if V paired with inner product is an inner product space, all right, then we said that S, a subset of V, is orthogonal if for all x comma y we pick from S, we find that the inner product of x and the inner product of x and y is 0. I guess I think I usually say x not equal to y. All right, anyway. So this is orthogonal. And so there's many wonderful theorems. Before I forget, what is the difference between orthogonal and orthonormal? S is orthonormal. Yeah, if S is orthogonal and each x in S has the norm of x, which, by the way, is the square root of the inner product of x and x, right, equals to 1. This is an orthonormal set. So pragmatically, like a nice formula, if we have S equals to, let's say, V1, V2, Vn, then S is orthonormal if and only if the inner product of Vi with Vj is equal to the Kronecker delta Ij, which I'll remind you is 1 for I equals to j, and it's 0 for I not equals to j. So if a set is orthonormal, that means that the inner product of two vectors in the set is 0, unless they're the same vector, in which case the inner product works out to 1. So before I get into any kind of general theoretical this and that, let me just give some examples of orthonormal sets. How about Rn and S equal to E1, E2, En, right? What is the dot product of Ei and Ej equal to? I mean, that's our standard quote-unquote inner product here, right? But my larger point is that this is just Kronecker delta Ij, right? So the standard basis is an orthonormal basis. Oh, basis. What's an orthonormal basis? What would an orthonormal basis be? I defined orthonormal set. I didn't define orthonormal basis yet, did I? What would an orthonormal basis be? A minimal spanning set for a vector space which is also orthonormal. Yes, or in other words, it is a basis which is orthonormal.
What a definition.
Right. I'm just saying, what's an eigenbasis? It's a basis of eigenvectors, right? These things matter, because I ask you questions about these things, and if you don't have a clear mind about what you're being asked, it could be problematic too.
With that logic, then what is the basis?
Cn, and again, S equal to the standard basis, right? So in this case, Ei, Ej, again, is Kronecker delta Ij. But this is the one I'm talking, this is the one, remember more generally we had ZW, was like Z1, W1 conjugate, Zn, Wn conjugate. So it's not the same example as the previous one, it just kind of looks like it, but it's not, right? Again, orthonormal with respect to this complex inner product. 3, for Rn by n, right? If you look at, the set Eij, right, such that 1 less than or equal to I comma j less than or equal to n. In other words, this is the usual, unit matrix basis, and we could give it the lexicographic ordering, right, like we usually do. So it's a basis, it's an ordered set. Well, this is orthonormal with respect to the usual Frobenius inner product. Let's work that out. So Eij, comma Ekl. How did we define this? It was defined to be the trace of Eij Ekl transpose. So let's see here. How's that going to work? That's going to be the sum. Let's say I need another letter, A. A equals 1 to n of Eij, parentheses, Ekl transpose. All right. All the AA component of that, right? That's the trace. We do like the 1, 1 plus the 2, 2 plus the 3, 3 plus the 4, 4 plus the 5, 5 plus it, so forth. So what have I done?
Nothing, sorry.
Oh.
My initials are up there.
Oh, your initials are up there.
Ekl.
Oh.
I heard you say it and I was like, whoa. She's important now. She's on the board. I'm sorry.
That's good. That's good. I mean, I've had much worse experiences in a linear algebra class. Once I was expanding the cofactor expansion of a particular 3x3 matrix using, I forget, like A, B, C, D, E, F, G, H, I. And I happened to spell a swear word.
How?
I don't know, but after I'd written it on the board, and before I realized what had happened, there were phones out and pictures taken. This is before I was videotaping classes. I'm not going to say the word. Come on, you guys.
Can you spell it out for us?
Yes, I will. I won't say it, but I'm going to spell it. That makes perfect sense. Let's see here. So, let's see here. I will tell you this much: the plus was used as the T. All right. Let's see.
I know. That's a good guess. I like that one.
What have I started? What have I started? All right. So.
It's Bob Smiley's fault.
Bob Smiley's fault. B equals. Do you guys get demerits, or do you get, what do you get?
It's a point system,
Points?
but I don't have an RA, so it doesn't mean you can't keep it down.
All right. So remember that we're looking at the product of matrices, and remember we defined how to multiply matrices. You like that, right? I mean, I have to sum over the B sums over n. I'm multiplying these matrices. I'm almost got there. This is almost surely a foolish use of class time, but I'm this far in, so we're going to keep going. So when I hurry through the Gram-Schmidt algorithm here in a second, you'll know why. Gram-Schmidt algorithm. Let's see here. So this is EKL AB, right? Because we take the transpose. So the transpose flips the indices there. And then finally, we have gotten down to the level of components. And remember how we defined, how did we define the matrix unit? What was the definition? Remember? Eij AB would be Kronecker delta IA, Kronecker delta JB. So I get Kronecker delta IA, Kronecker delta JB, Kronecker delta KA, Kronecker delta LB. So many Kroneckers.
Question. What is it? Yeah, what is it? What are you saying? Like, why don't it just like, yeah, but why? Isn't that just like a piece function? Is it just like a delta, like, is that just like the name of it?
It is the name. I mean, this is, I'm probably missing some sort of,
Was it someone's last name or something?
yeah. So some dead European, you know,
Someone decided.
one of the many patriarchs of math. What can I tell you? Math's very patriarchal. Let's see here. Listen, the Kronecker delta is the natural enemy to the finite sum. And so what happens here is the sum over A just squashes to a sum over I. It puts it. Okay, so the thing is here, I, J, K, and L, these are all free indices. That means that they survive. All right? And so we keep the free index. We get Kronecker delta. Let's say this. So this is just 1, and B gets set to J, so that's just 1. So what I'm trying to say is I set A equal to I, and I set B equals to J, and it just leaves me with Kronecker delta K, A was equal to I, Kronecker delta L, and B was equal to J. What does that say? Going back to the, that's only non-zero if what? So this is equal to 1 if I equals to K and J is equal to L, and it's equal to 0 otherwise. Which is what we want. That says that when these match up, you get 1, and otherwise they don't. In other words, this is an orthonormal basis. The same calculation shows you that that's orthonormal for n by n complex matrices. Okay? Now that I got that out of my system, let me prove some theorems for you. S orthogonal. Did I already prove this? S orthogonal and non-zero implies linearly independent? No. Okay, orthogonal and 0 not an element of S implies S linearly independent. So everything I'm saying here, let me just, could you please understand that this lecture is given in the context of subsets of a given inner product space with an inner product where we're inducing the norm by the inner product as we discussed last class. I don't want to keep writing that and everything, but that's our assumption here. So this S is a subset of a inner product space, all right? And that's the orthogonality I'm referencing. Okay, so let v1, v2, vn be be elements of S, and consider, you know, c1 v1 plus c2 v2 plus cn vn equal to 0. To show that this is a linearly independent set, we must show what? Yeah, we need to show all those constants are 0, right? So what we're going to do is consider, you know, v, let's say j in S. Well, vj in S for some 1 less than or equal to j less than or equal to n. So one of these, right? I want to pick an arbitrary one, though, all right? And calculate the inner product of c1 v1 plus c2 v2 plus plus cn vn with vj. Right. If you'll allow me this small manga-style calculation, of course, this should be equal to 0 because right? I mean, whatever we're calculating here must be 0 because the inner product of 0 with anything is 0. And then I'll use properties of inner product. So I got like c1, v1, vj, plus Eventually I get to cj, vj with vj, plus cn, vn with vj, using the additivity and homogeneity of the first entry of the inner product, yeah? Part of the axiom. And what am I looking at? What am I looking at here? What can we say about anytime we're looking at the inner product of, say, vi with vj, where I and j are not equal, what happens there? Because we're assuming S is orthogonal, right? I guess I should really, you guys are like, I take 5 points off your proof. You didn't say assume S orthogonal, right? I should say that. This is always an issue with proofs. If you read proofs in books cost money to make, and so oftentimes the proofs are shortened by the blanket assumption that whatever the hypothesis of the theorems are, those are understood at the start of the proof, right? But when you guys write proofs, we kind of like you to write it out. What's that? Spread would have your head. Yeah. Yeah. But then you get your breakfast, so it's okay. It's all right. It works out in the end. Or brunch. Brunchfast? Brunchfast. Okay, very good, very good. So what I was trying to get at here, guys, is just that most of these things are 0, except when they're not. Right? This is 0, this is 0. The only thing here which is not 0 is that, right? Because an orthogonal set doesn't say that the inner product of the vector in itself is 0, right? What is the inner product of a vector in itself? 1. I didn't say that here. I didn't say that here. The inner product of a vector in itself would be the norm squared of the vector, right? So remember that the norm is the square root of, the norm of x is the square root of the inner product of x with x. So that means that this is the length of vj squared. And so what we have is 0 times cj times this is 0. But vj is by assumption not equal to 0. So that means that the length squared of vj is also not equal to 0, which implies that cj is equal to 0 for arbitrary j. Right, so therefore c1 equals to c2, cn, they're all 0, which of course gives us that S is linearly independent. Notice that it is very important that we have the assumption that 0 is not in S. If 0 is in S, this argument falls down, right? Question?
So is orthogonality a stronger property
Yeah,
Okay, yeah, so,
I would say so. The question was, is orthogonality a stronger property than linear independence? In my book, yes. Because it's nicer. I mean, it's more structure. There are many, many more, in some sense, linearly independent sets than there are orthogonal sets. Let me make that more precise. If you take any matrix in GL, let me just be specific to our n by n. Let's think about n by n. If you take any matrix in GLNR, in other words, A inverse exists, yeah? In other words, the determinant of A is not equal to 0. That gives an invertible matrix, and as such, if you take the collection of column vectors forming A, that's linearly independent. So column, I of A, I equals to 1, 2, delta n, is linearly independent. In contrast, if I want an n by n matrix of orthogonal vectors, I can't do that with just any old linear. I mean, there's a specific subset of matrices which will have orthogonal column vectors. Or let's limit the discussion to orthonormal. It turns out that if you want the columns in a matrix to be orthonormal, then that kind of matrix is, quote unquote, annoyingly, an orthogonal matrix. An orthogonal matrix has orthonormal columns. So this is part of a larger discussion. I was not planning to say this right now, but since the question was asked, I'm going to say it. So we will later define ON R. So this is A in Rn by n, such that A transpose A equals to the identity matrix. This is the so-called orthogonal group of n by n matrices. We can prove that the columns of an orthogonal matrix are orthonormal. But this is a much smaller collection of things than GLN. Lots and lots of invertible n by n matrices. It's considerably less orthogonal n by n matrices. Like the dimension of this space as a vector, as a manifold, is n squared. The dimension of this as a manifold is smaller. It's, I mean, you've got so many equations here that are limiting the size of your space. Anyway, let me stop there. But I think I've given too lengthy an answer to your question, because we must move along here. All right. So corollary to the theorem I just proved. Corollary. If S is orthonormal, then S is linearly independent. But there's more. Do you see why is that true? Do I need to explain? Let me explain. If it's orthonormal, that means that every vector in the set has length 1. Yep.
Does that mean each vector in the set is a unit vector?
Exactly. Each vector of the set is a unit vector. That's a perfect way to say it. Yep. Calc 3, yeah. That's what we're trying to generalize here. Okay, so another theorem I can share with you. If beta, V1, V2, Vn is orthonormal basis for vector space V, then x is equal to the sum I equals 1 to n of the inner product of x with Vi. AKA the coordinate vector of x with the beta in the beta coordinate system is just equal to x with v1, x with v2, x with vn. So proof, let beta and be as above. If x is an element of the vector space, then there exists C1, C2, Cn in the field, whatever field we're looking at, either the reals or the complexes, all right? Such that what? X is equal to the sum I equals 1 to n of Ci Vi, right? Because beta is a basis. You guys with me? I haven't said anything controversial yet, I think. Thus, the inner product of x with Vj is equal to the inner product of the sum I equals 1 to n of Ci Vi with Vj. So what happens there? By properties of the inner product, we can pull out the summation, yeah? We can pull out the constants, and what does it leave us with? The inner product of Vi and Vj. But what did we assume about beta? We assume beta is orthonormal, which means that the inner product of Vi and Vj is that strangely named Kronecker delta once more, right? And yet again, that squishes the finite. The only thing that survives this is Cj. Everything else is 0. Because I only get non-zero when I is equal to j, in which case we have Cj times 1, which just gives us Cj. J being arbitrary, we've proved the theorem. See, because I just showed you that the Cj, the Ci is given by this Cj is equal to the inner product of x with Vj for each j, which means that this right here can be rewritten as what? Right? And then, since you guys know the definition of coordinate vector, my AKA statement's not mysterious, right? Right? You will learn the definition of coordinate vector before the final. Just because I want everyone here to pass. Please learn the definition of coordinates in a way that you can solve problems when asked about them. All right, anyway. Whoop. Oh, that looks perfect for erasing. It's the right color. You can see my confusion, right? It's just it's pretty close, right?
There's an eraser right there.
Erasers are so, yeah.
The color's similar.
Pretty similar. All right. But, it takes hundreds, if not thousands of hours of lectures to attain this, this is like a fine wine, Oh, I'm sorry, we wouldn't know about that. It's like a... He does? Well, I'm not going to say anything more because I don't want to edit this video today. All right, let's see here. Yeah. It started out white, yes. That's why I go. Okay, example. if 1 over the square root of 2, 1, 1, 0, and 1 over the square root of 2, 1 minus 1, 0, and then finally 0, 0, 1. Sorry, I'm reverting to Calc 3 notation all of a sudden. My lingo.
I understand this.
You understand?
Leave it.
Leave. I need a minus there as well. All right.
Okay.
If V is equal to ABC, then find the coordinate vector of V with respect to the beta basis. So with the theorem I just proved, this is a piece of cake, right? So the coordinate vector of V with respect to the beta basis is just equal to, V dot with, well, let me follow my definition here. V dot 1 over the square root of 2, 1, 1, 0. V dot 1 over the square root of 2, 1 minus 1, 0, because this is the inner product in this context, right, the dot product. And V dot 0, 0, 1. I mean, that's the theorem implemented for my example. What is the dot product of ABC? So we've got A plus B divided by the square root of 2, A minus B divided by the square root of 2, and C. There you go. That is the coordinate vector with respect to that beta basis. All right? Okay. Now, another thing we can say here, if beta is an orthonormal basis for V, I could, this theorem equally well applies to like a subspace of a vector space, right? If you've got a subspace of a vector space and you have an orthonormal basis for the subspace, we also still have the same formula, right? Like if you had an orthonormal basis for a subspace, that would also work, the theorem. Because after all, a subspace is a vector space in and of its own. And remark, if W is a subspace of V, and this is an inner product on V, then W paired with the inner product restricted. I mean, we don't even write this half the time, but you can restrict the inner product to W in the sense that it's a mapping from W cross W to the field where, how would you define, how would XYW be defined? It would just be XY for all XY in W. What I'm trying to say is it's a simple exercise to show that if you have an inner product on a whole vector space, and if you restrict to a subspace, it's still an inner product. Okay? You still have all of the axioms descend naturally. Just a comment. That's important in terms of what I just said, in knowing that the theorem I just erased equally well descends to a subspace. If I have an orthonormal basis for a subspace of a vector space, I can also calculate the coordinates of a vector in that subspace with respect to taking inner products of the subspace basis just the same. Okay. Another theorem which is important to us is that if beta is orthonormal, basis for W equal to this, I'll state this theorem for a subspace, right? This is all happening inside some larger vector space conceptually, okay? And in that larger vector space is inner product. All right? Great. And x is equal to, say, x1 v1 plus x2 v2 plus da-da-da-da plus x, well, xk vk, where I'm being specific here. I want beta to be v1, v2, vk, okay? Then the length of x squared is equal to x1 squared plus, oops. Uno momento. Modulus of x1, absolute value of x1 squared, absolute value of x2 squared, plus absolute value of xk squared. Here, the absolute value of xi is either equal to just ordinary, absolute value in R, or it's the, like the absolute value of, how can I say this? I guess I haven't used alpha and beta. Alpha plus I beta. Absolute value of alpha plus I beta would be the square root of alpha squared plus beta squared. Now, I don't always use that terminology. I like to say that that's the modulus of the complex number. It's the length of the complex number, alpha plus I beta, but that's what appears here. So this is another theorem that is known for orthonormal sets, which is very nice, right?
Does this theorem apply for all the natural numbers or just
Squared value.
you're saying like the length of x squared is equal to this is the components of x1 squared plus x2 squared plus yada yada yada.
Uh-huh.
Xk squared. Does that apply to like the length of x cubed?
Oh, no. This is just for the square. And let me show you why. So I will not prove this in general because, well, I'm lazy. But let's prove it for two things. All right, let's call the two things like v and w. All right, so suppose you have v and w and orthonormal. And let's look at x equal to, well, I'll tell you what, I'll look at z equal to xv plus yw. And I want to look at the length of z. The length of z squared is what? It is the inner product of z and z. But z is xv plus yw, comma xv plus yw. And here, of course, x and y are elements of the field that we're working over, either the reals or the complexes, okay? Then what do? Well, properties of the inner product say that this is equal to x bar xx plus x y bar vw plus y x bar wv plus y bar ww. So here I'm using the so-called sesquilinearity of the inner product, which is like, sesquilinearity means like 1.5 times linear. It's additive in both the first and second slots, but you pull out the conjugate of the second slot, which is, it's not quite linear in the second spot. So it's kind of half linear, so 1.5 linear, sesquilinear. But now, if the field is the reals, we already have x squared, xy, yx, and y squared here. But in the case that it's a complex field, what we're looking at, the product of a complex number and its conjugate is the absolute value squared of the complex number. So what you're looking at is the absolute value of x squared plus, well, the absolute value y squared, and that's it. And how, what do you mean? But, hey, what did you do? Well, this is 1, this is 0, this is 0, and this is 1 by what? By Kronecker delta, but by orthonormality of v comma w. So what this says is that if we use an orthonormal basis, then the coordinates with respect to an orthonormal basis behave like normal coordinates that we're used to, like Cartesian coordinates, right? You were raised on orthonormal coordinates. You didn't even think about it, but the Cartesian coordinates are orthonormal coordinates. Regular, garden variety, Cartesian. Yeah. Cartesian, yeah. Not the, we brought not the Cartesian product back into the discussion. All right, guys. Okay. So I hope I've made the case at this point that orthonormal sets are wonderful, have beautiful properties, very convenient calculationally. The question is now the following. Can we take a set which is not orthonormal, and can we modify it and convert it into an orthonormal set? So this is the task. Can we take S, let's say S1, S2, Sk, a subset of some inner product space V, and find S, I'll call it prime prime, S prime prime, a subset of V, such that the span of S is equal to the span of S prime prime, and S prime prime is orthonormal. The answer to this question is yes, if we do need to make an assumption about S. We'd like to assume S is linearly independent. All right. If S is not linearly independent, then this isn't going to work out. But let's assume S is linearly independent. We do make that assumption. And so the way to do this, all right, is with something called the Gram-Schmidt algorithm, which I refer to as GSA, Gram-Schmidt algorithm. So I took my abbreviation and abbreviated it. There you go. So I'll get you started. S1 prime prime is S1 hat. In other words, it is, as was brought up by one of you guys, the unit vector in the direction of S1. So specifically, that's 1 over the length of S1 times S1, where the length of S1 is the square root of the inner product of S1 and S1. So you start like that. Then the Gram-Schmidt algorithm says next, you look at S. I'll say S2 prime is equal to S1, excuse me, S2 rather, minus, all right, minus the inner product of S2 with S1 prime prime times S1 prime prime. So what this does is you're subtracting off the piece of S2 which is in the S1 direction, in the first direction, in the 1 prime prime direction. You can prove, okay, and so this gives you a vector, S2 prime which is orthogonal to S1 prime prime, but not necessarily normal. So then you take this and then you go, okay, so then S2 prime prime is S2 prime hat. In other words, you go 1 over the length of S2 prime times S2 prime and that defines S2 prime prime, a vector which has length 1 and is perpendicular to the first vector in your set. And then you do S3. S3 prime, you start with S3, you subtract off the piece which is in the second direction. So you subtract off S3, S2 prime prime, S2 prime prime, and then you also subtract off S3, S1 prime prime, S1 prime prime. So what you're doing is you're taking the third vector and you're subtracting off of it the part of it which is in the second or the first directions. Yeah.
Should those first two equal like S2 prime? Should that be S2 prime prime?
No. The prime is not normalized.
Okay.
So that's why I have a prime prime, is to, my primes aren't necessarily, I mean, the first one doesn't, there's no prime step in the first one because you have a vector, you normalize it. That's all there is to it. There's nothing to subtract off. But everything after that, I always have to, there's one step to subtract the piece, which is in the directions that were already explored before. And then once you have that, you have to normalize it. So it's a two-step process after the first step. Sounds like some sort of country line dancing or something. Again, we wouldn't know about that. But I wouldn't know about that. I wouldn't know about that no matter where I worked. But anyway, just saying. Country music evil. All right, anyway. One of the many problems with Hannity, what can I tell you? But
What? Can you say that again?
this is one of the many problems with Hannity is his unnecessary love of country music. It's like Sean Hannity. You guys don't know who that is. That's interesting.
Do you normally watch the news?
I once went on a youth trip when I was a teenager to Washington, D.C., and I remember a girl in my youth group asking me, "What's this Pau Mia?" Yeah, now,
Oh my god.
that would be okay for you guys. But you got to understand, when I was like a teenager, we were like fresh in the middle of Chuck Norris's onslaught of, I mean, how many movies did Chuck Norris make about the POW/MIA issue? There must, like, every Delta Force movie practically, right? I don't know, I can't remember which ones, but so many. Anyway, I digress. So this vector S3 prime is orthogonal to the previous two, but it's not normalized. Then you put a hat on it. Right? This keeps going, but it has to terminate by the time it gets to k, because you can't have more than k linearly independent vectors in a linearly independent set that's formed with the basis of k vectors. And we know that orthonormal implies linearly independent, right? So it can't go past step k. And also, if you take a more nuanced view of what I'm doing, you can prove that at no point does it cycle back to wherever it already went. Do you guys know what the next step would be? What would S4 prime be? Okay. So it's always the fourth one that goes, the one that you're fixing goes first, and then you're ripping off components. It doesn't really matter which order you put these in. You just got to make sure you get them all. And this is the Gram-Schmidt algorithm. Now, so, come on. Did I guys tell you the, have I told you the, only 16? Is that right?
What?
4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's a ton of, there's a lot of people missing today. Oh, is it the CFA? Come on. Try not. All right. Again.
Yay!
Or don't. I mean, I don't care. Now, let's see here.
Do it again. Wait, not again. Gotta wait for 16. Oh, it's in there.
Class is pretty much over, but I wanted to show you a gory so this example in the notes, I start with vectors v1, v2, v3. I run Gram-Schmidt on them. I create this v1 prime prime, v2 prime prime, v3 prime prime by going through the steps I just did. As you can see, the resulting vectors are orthonormal. And also, that calculational process would take me 20 minutes to write out. Here's an example of a 4x4 system. Again, I Gram-Schmidt. Let's see here. This is a more interesting example. I think I do this in the video from next time. If I didn't do it in the video from next time, I did it in the video that was posted to mirror this class. You can also apply Gram-Schmidt in sort of more interesting cases like continuous functions from -1 to 1. You can, if you Gram-Schmidt the monomial basis, you find out this is not orthogonal or orthonormal, but if you do Gram-Schmidt to this, you generate what are called the Legendre polynomials, which are interesting things. So these are orthonormal with respect to that inner product. So anyway, I'll say more about this when we come back together.
On Wednesday, right?
On
We're not here on Monday.
okay, so yeah, can you hit the camera?